Yeah, thank you, Prof. So I'm Saptarishi. I graduated from Ashoka with a degree in CS in May, and now I'm working as a pre-doc at the center. So this is just an overview of the weather and climate work that we've been doing at the center. I'll take the weather part, and Atish will take the climate part. We have a team consisting of me, myself, Manmeet, who's at UT Austin, Professor Partha, Atish, Naveen again at UT Austin, and we've also had Sagar and Mihir join recently. So my work on weather is about fine-tuning the GraphCast neural weather model to India precipitation data. So the overview is that we have the GraphCast weather model and we want to optimize it to India precipitation through a satellite-based data set. We fine-tune it regionally and with newer precipitation-specific data. This is because global models focus on many things, and hence they could be suboptimal on specific regions and variables, especially precipitation. So we focus GraphCast to India and the loss to a precipitation specific to India derived from this newer data set. And we allow the weights of the model freely change to get better predictive performance for Indian precipitation. And with this idea, the like simple idea, we got better predictive performance relative to the original model. And for precipitation over like many simulations like initialization dates. And this warrants exploration of fine-tuning the models to more data sets specific to particular use cases. Because then we'll be able to create more kind of bespoke models catered to like relevant use cases. So just some background, I'm sure like most people know about this, but traditional weather modeling and NWP is a science of simulating the weather with computers and making predictions based on current weather conditions. Now, physics-based NWP uses the initial conditions of the atmosphere and various dynamics equations to estimate the state at some point in the future. Now, machine learning for weather modeling has come up in the past decade or so because of the rise of the three so-called pillars of AI. That's data, because weather modeling generates a lot of data through reanalysis or just observations in general. And we've also had new algorithms and architectures like GNNs, transformers. And the third pillar is compute. With the rise of GPUs and more efficient methods of compute, we can leverage these algorithms operating on this data to have like good models for weather. Now we leverage these and we create data-driven methods which instead of using explicit physics-based equations, they try to learn patterns in the past weather to try to extrapolate to the future. Now, after training, these models can roll out a forecast, as a lot of my previous speakers have pointed out, much faster than NWPs. Now, this is just a schematic. NWPs take initial conditions and they roll out a physics simulation to get an ensemble of predictions if you're perturbing the initial conditions. But the neural network-based models takes the input data, it tries to learn a distribution over it so that when we roll it out in the future, it tries to emulate that distribution. And over like the last 5 years, lots of state-of-the-art models have come out, as has been covered again, such as GraphCast, Neural GCM, Pangeo, ForecastNet, Prithvi, and they've achieved performance, at least on a lot of metrics, comparable to state-of-the-art numerical weather predictors of various countries. Now, for fine-tuning weather models, there's been more recent, relatively little work. For example, there was a work out of Canada which fine-tuned GraphCast to use with their analysis or prediction system. There's also been the exploration of low-rank adaptation and fine-tuning to HRES information that's been used for region-specific fine-tuning. And also, if you pick one model, there's the ClimaX model by Microsoft and UCLA that I think Aditya talked about yesterday, and various fine-tuning applications in various sectors are also being explored for that. Now, our motivation was that India has unique weather patterns that global ML models like GraphCast may not capture out of the box, especially for monsoons. And if we take additional data sets and we fine tune GraphCast to India, this can improve predictive power because the models originally are trained to optimize globally and may not have knowledge from other data sets, such as the data set we used, encoded into the parameters. So if we encode them and like fine tune on it, we could get better predictive performance on these data sets. Now, the first data set is, of course, what GraphCast is trained on. That's the ERA 5 reanalysis, 0.25 spatial RD temporal resolution from 1940, various weather variables at different pressure levels. And this, if for those who don't know, reanalysis essentially is combines observations with climate models for a very like one-line description to kind of fill in the gaps of what happened in the atmosphere in the past. And it's also known through various studies to have specific biases especially for precipitation. Now, the data set that we used for fine tuning was the iMerge data set that I think Siddharth covered earlier also, which is available to us as a point 0.1 spatial and daily as well as every 30 minutes data from the integrated multi-satellite retrievals from NASA, which estimates precipitation from satellite information. Now, this is iMerge is usually considered to be a good gridded data set for precipitation in the field. So you just take all these satellites, information that are there, they estimate it, and we get data from iMerge at 30-minute temporal resolutions. And there are like multiple runs. There's the early run, late run, or the final run, which have different latencies on which we can access it. For fine tuning, we mostly use the final run, which is the most like best quality iMerge dataset. So coming to the model, GraphCast is a graph neural network with an encoder, processor, decoder architecture, which I'll come to later. For making a prediction at time t plus 1, it needs the weather state at time t and time t minus 1. So it covers a lot of variables taken mostly from the ERA 5 reanalysis. These are the mostly the atmospheric variables, which we have at various pressure levels, the geopotential, specific humidity, temperature, etc. And these are the pressure levels. 37 pressure levels are there. But we also have a model with 13 pressure levels, which are highlighted in bold. I don't know if you can see it, but there are 13 like which take a subset for more computational efficiency. Now, these are the single variables which are only there kind of on the surface. That's precipitation, temperature, and all the others. And we also have other things like forcings, static variables like latitude, longitude, local time of the day, how much of the year has progressed. So GraphCast just takes all of these, and this is the data set that it mostly works on. Now, just an overview of the model. This is the input weather state that it takes. And to predict the next weather state, what the GraphCast model does is it divides itself into an encoder, processor, decoder architecture. The encoder takes it from the grid into an intermediate mesh representation. And then on that mesh representation, processing happens through the graph neural network message passing to figure out the relationships between all the nodes. And then once the relationships are figured out, that's decoded back onto the original grid on which the weather like dynamics actually happen. And there's also a multi-mesh that they use. It's not just one mesh. They have a mesh with different like resolutions, like the most M0, it's the coarsest icosahedron, while if you go to M6, it becomes a very close approximation of a sphere. And then once it's learned all this, it's able to roll out a forecast auto-regressively for how many, like around a week or so. Now, the training loss is a bit of a long loss function. So you take a particular, so in the 0.25 resolution model, you have 0.25, 0.25 grids. So that's 1440 into 721. Each node has around 227 variables because 37 pressure levels and atmospheric variables. So it becomes around 227 million like things that are there. The whole group, that's 1440 to 720. So if you multiply everything, it around comes to 225 million like things on the grid. Yeah. Y- Yeah. Yeah. Then there's the loss function on which GraphCast operates on. So for a particular, yeah. Yeah, so they're connected, but the weights of them are decided during training to figure out which one is affecting the other. Uh, because whether like the way they've implemented it, they left the network to figure out which nodes are related to each other. So it could be that it's learned something where something on the opposite side of the world, like El Nino, is affecting it, but it's not mainly a climate model, it's still a weather model. So I doubt that is stuff is being learned. Yeah, because weather could be kind of like that. But mostly the weights that are learned are more close form thing because it's the weather model and not a climate thing. Yeah. Yeah, so like the multiple meshes that are there here. Yeah, so it's not like the mesh that's there, like India, like a node over India. It's like directly connected. It's like connected through like multiple jumps and hops and stuff like that. So technically, like you could like traverse it, but weather ke liye, for weather it doesn't really happen. Yeah, like a finer resolution over India, that could be. So the loss function, you take the batch, you take a particular lead time. GraphCast trained it for 3 days lead time, so they just average the loss over that. Then a spatial location, G 0.25 is just all the 0.25 degree grids. Then the variable levels, which is the pressure levels of the variable. And then you take what they call the inverse residual variance, which is just to normalize across all lead times. They also have variable level weight because for each variable, they assign a weight to that variable, which is something that we come back to in the fine tuning process. And we also have the area of the latitude longitude grid cell, which is just like the area of the each particular grid cell. And of course, we have the squared error between the predicted thing at a particular latitude longitude ij for this particular training batch at a particular lead time tau. Now, fine tuning GraphCast, what we do is we just restrict. Yeah. Yeah, it's doing a 3 day forecast. Over that, it's trained on. Like it's trained to make 3 day forecast because the loss is calculated over the whole thing. Yeah. Like that's how they make a forecast, but the loss is calculated after they've made enough rollouts to give a 3 day thing. Yeah. So we restrict the loss to India for precipitation, and the weights are allowed to change to focus on the IMS precipitation loss for India. Now, GraphCast is trained from 1979 to 2015, but for the fine tuning, which is in the next slide, to make it fair for the base model, because we didn't want to use newer data post 2015 for fine tuning, we chose IMS data from pre-training period to make it give it a fair comparison with the base model, and we incorporate the IMOS data to the ERA5 format so we can just fine tune it to this IMOS data that GraphCast hasn't seen. So we have the GraphCast model that's learning the ERA5 global patterns, and we just take those weights, we incorporate iMerge into the ERA5 format for precipitation, and then just try to reduce the loss over that over this training period that we have. So we had to upscale iMerge. We used the 1 degree GraphCast model for computational reasons. We replaced the ERA5 precipitation with these updated values. The fine-tuning period that we chose was also relatively short. The monsoon months of 2012 and 13, plus June and July 2014. And this was chosen, as I said, original GraphCast period for fairness to the base model when comparing. Now the evaluation period we chose was August and September 2015 and the monsoon of 2015. And we use like just a tooling thing, we use JAX, Optax, and like Dask for parallel processing. And for evaluation, what we did, we can't just run one forecast and say that if we got a better fine-tuned thing, then that's better than the base model. So we initialized the base and fine-tuned models for all these evaluation dates post the training period, and we rolled out a 7 day forecast for each. Now the metrics were calculated for each forecast, aggregated across each lead time in 6 hour intervals, which is the granularity at which GraphCast makes a forecast. And these metrics were of course like calculated for precipitation since that's the variable we were focusing on. Now, this is a graph that we got for the RMSE. The orange line is the base, the blue line is the fine-tuned model. And what is obvious is the periodicity, which if you plot the average precipitation over India is because of the diurnal cycle. So each lead time is initialized at 12 a.m. So we see a spike at a particular day, point of time in the day. And which when the precipitation is higher, we also observe higher errors because there's more stuff kind of to get wrong. And this is true for both the base and fine-tuned models. But we do see a decrease in the error this when we evaluated IMERGE. Yeah. Yeah, on whatever evaluation period we are. Then this is for we evaluated on IMERGE only because we are fine-tuning it here. I haven't put HRES on this plot, but the base model for GraphCast, like when I was running experiments, it did show improvements. Like it showed better than HRES for precipitation over India. It was like 10 to 20. Yeah. Ye- Yeah, the base model for precipitation. Yeah, all India average. And then this is just the another metric, the anomaly correlation coefficient. So this kind of removes the bias of the climatology and figures out how much the model is actually learning the variabilities and stuff like that. And over here, a higher thing is better. So the fine-tuned model has a higher ACC across all lead times, and the percentage improvements is also being seen over there. Now, this is just a sample visual map at some particular lead time that we chose in the evaluation period. Yeah, so in this, it's because I haven't plotted the precipitation here, but in this graph, it's because of the diurnal cycle of precipitation. Each evaluation date is initialized at 12 a.m. And at each lead time, you see the precipitation go up. And since there's more stuff to get wrong, the error also goes up. And that's true for both the base and fine-tuned models. And this is a sample thing where the RMSE, like compared to the base model. Okay, so like that's the bottom graph, I guess, but that also shows a variability, yeah. Because the extremes, whenever the error is rising, you see a difference in the error. Then this is a sample where over like the Rajasthan Punjab area, you see the base model making a significant over prediction of what the rainfall could be. And the fine-tune model kind of corrects for that, focusing on iMerge. This is a sample to show what the fine-tune versus base prediction looks like. This is, I haven't put it on this map, but I remember it's like the 144-hour forecast from in the first week of August in the evaluation period. Yeah, because it's pre-training period though, yeah. Now, just to conclude, I'll just give an overview of some future work that we plan on doing. Since, yeah, yeah, the disaggregate. Yeah, the disaggregated, like the monsoon homogeneous regions is actually taken it and then evaluated for each of those regions also. Yeah. So I just did it for all India because in the original GraphCast paper, they took the whole world and gave a metric. So I thought like since we're fine tuning to India, I could just do India. Now, some future work, since we fine-tuned this IMOS data set and we're observing an improvement to the base model. So it is kind of warrants, as even Aditya was suggesting yesterday, to explore further data sets to which we can fine-tune such global models so that we can learn the distributions and kind of incorporate more ground truth information instead of just relying on reanalysis. Now, another thing is that this is a 1 degree model and someone have a question? Yeah. So we could downscale these course forecast with diffusion and other methods for downscaling and get better, more finer forecasts because those are more useful for real life like applications and for using these forecasts in an actually useful manner. Yeah, so diffusion can be used for downscaling and also ensemble forecast. Since that's also a project that a center does is focusing on the tails of distributions through diffusion. Through ensemble forecast also like the models like GenCast and ULGCM, which can through AIML methods make ensemble forecasts. So that's also something that we plan to do. Another thing was real rollout of real-time forecast. We initialize it with the ERA5 data or because of the 5-day delay, the more operational thing as Professor Ravi had suggested, and that would give us a more like real-time forecast system which we can just keep on rolling out on like a dashboard for the center or whatever. And there's also bias correction of forecast output as Siddharth had spoken about. And this can be done through some ideas that we are exploring is region-wise boosting. If errors are accumulating in a particular region, then focus a model to that region and then bias correct those errors depending on where the errors are accumulating region-wise. So this is just what we plan to do in the weather field for the center. And now I'll just invite Atish to cover what he's working on in climate.
See, this ECMWF, I have a message from Peter. He's telling that yes, 0.25 degree initial condition is free. Free. Yes, it's free, but not the point 0.1. But 0.25 also is good, 25 kilometers.
All right, so next speaker is Atish. I should add, well, yeah.
I think it's yeah, 20 years approx. Yeah, that's what we do plan on doing. I should have mentioned this also because the fine-tuning period, as I mentioned, was especially short. So we do plan to use as much data as possible. We were also we wanted to first work on the point to 5 model so that we get a finer resolution forecast because then we can use a more finer resolution iMerge as well. So before working on like extending the iMerge period, we're working on trying to get the point to 5 model to work on like whatever compute we have.
So I should mention that the fine tuning and training is for a couple of years because we only have 2 GPUs. If Sapta had 20 GPUs, he could have done a lot more. So that's a big constraint. Thank you. So yeah, I should just add, Atish is doing his PhD at Triple IT Delhi